Question 2 of tutorial 5. This is our differential equation. Once again, we solve the complementary equation and we obtain this general solution yc. Now we need to consider observations on g of x. G of x is an exponential function. So when we take derivatives of higher order, we will always have e to the 3x appearing in the formula. You can see that when we take the kth order derivative of g, what we should get is e to the 3x, and every time we differentiate, we need to bring down a copy of 3 when we differentiate 3x. So we should get a formula of this form: constant times our original exponential function g of x. Therefore, it would make sense for us to define yp as a constant a times e to the 3x. In this way, when we differentiate yp further and compute yp prime and yp double prime, they will be of the form b times e to the 3x, where b is a constant. Then, when we substitute everything into our original formula, yp double prime is constant times exponential. Yp is also a constant times the same exponential, and taking such a linear sum would certainly give us a constant times the same exponential function. So we will choose yp to be a times e to the power of 3x. When we do the substitutions, making this choice, we have that yp prime is given by this expression, yp double prime is given by this expression, and clearly in all cases we have a constant times the same exponential function. We make our substitutions into our original differential equation, and what we want is that upon substitution we obtain g of x on the right hand side. Yp double prime is 9a e 3x, and yp is a times e 3x. So substituting will give us on the left hand side 18a e 3x, and by comparing coefficients we see that 18a must be equal to 1, and therefore a equals to 1 over 18. So we have found the value of a, and therefore we can write out the general solution. Taking yc will give us this, and yp from what we found is 1 over 18 e 3x, a taking that particular value. C1 and C2 are our real arbitrary constants, and this solves question 2.